Hello everyone, today we're gonna learn about tree data structure. There are quite a lot of things to talk about tree data structure, so I'm breaking it down into 5 parts. Today's tutorial is part 1, and we will talk about tree and binary tree. This tutorial is a part of the data structures and algorithms class. An important note, this tutorial uses many concepts like nodes and links, which are presented in the previous tutorial linked list. So if you haven't learned about linked list, please stop here. Go learn linked list before you continue. Today we're gonna learn about 3 main kinds of trees. The tree in free form, binary tree, and ultimately they're gonna lead us to binary search tree. Because binary search tree gives us an excellent time complexity in number operations like insert, delete, and search. But before deep diving into binary search tree, we're gonna also learn about tree in free forms and binary tree. In this picture, I have 3 kinds of trees. A tree in free form, a binary tree, and a binary search tree. In general, we call these 3 our tree data structure, and they share basic building blocks. Just like linked list, we have nodes and linked. For example, in this tree, we have node 1 is pointing to node 2, and node 2 is pointing to node 5. And in this binary tree, we have node 5 pointing to node 3, and node 3 pointing to node 8. In this binary search tree, we have node 6 pointing to node 4 and node 4 pointing to node 1 and 5. All kinds of trees have very similar building blocks. They are nodes and links, just like linked list. But as you can see, unlike linked list, a parent node can point to multiple child nodes. Because of this reason, the tree data structure looks like a tree, but it's upside down. And linked list is actually a tree with each node has exactly 1 child. So you can imagine if I remove this part of the tree 961, this tree remains 538, and it looks exactly like a linked list. Now let's see some more similarities and differences between these trees. For a tree in free form, a node can have as many child nodes as it wants. For a binary tree and a binary search tree, a node can only have maximum 2 child nodes. And with binary search tree, we have a special constraint. Whenever we insert the data into the tree, that is, the right child has to be bigger than the parent node, and the left child has to be smaller than the parent node. As you can see here, 8 is bigger than 6, and 4 is smaller than 6. This constraint will lead to very useful binary search tree operation performance, and we're gonna learn about it in details later. There are many ways to extract useful information out of the tree. Most of them are applicable into any kind of trees. Some of them are specific to binary tree and binary search tree. To extract useful information out of the tree, we can have breadth first search, depth first search, in order, pre-order, or post-order traversals. And we're gonna learn all about them later. The application of tree data structure can be seen all around us. Some familiar applications are human ancestry tree, internet browser DOM modeling, syntax parsing for a programming language, and so on. Now let's talk about some terminology when we talk about a tree. So a tree always have a root node. The root node is the first node that you add to a tree. For example, for this tree is 1, for this tree is 5, and for this tree is 6. Then we have a leaf node. The leaf node is the node that doesn't have any children. For this tree, that's gonna be 5, 3, 6, and 7. For this binary tree, that's gonna be 8, 6, and 1. And for this binary search tree, that's gonna be 1, 5, and 10. And then we have tree size. The size of the tree is the total number of the node in a tree. For example, this tree has 7 nodes, so the size is 7. This binary tree has 6 nodes, so the size is 6. And this binary search tree also has 6 nodes, so the size is 6. A node that pointing to other node is a parent of those nodes. For example, this one 6 is a parent of 4 and 8. And 4 is a child of 6, but 4 is also a parent of 1 and 5. Next, we have tree height. Tree height is the total number of levels of nodes. In this particular example, we can see that all the trees here have the height of 2. Next, we have the concept of a balanced binary tree. A balanced binary tree is a tree that has the left and right subtree of every node differ in height by no more than 1. That means if you imagine there's a line here that divides this tree into 2 parts. The left tree had the height of 2, and the right tree also had the height of 2. So the height in left and right subtree differ no more than 1. In this case, there's no difference, they are equal. Then we say that this tree is balanced. You should understand and remember this concept very clearly, because we're gonna have important application for it later. Next, we're gonna learn a little bit more about tree types and common properties. These are just a term to reference to a tree, so when you hear about it, you will know how a trees look like. First, we have full tree. For a full tree, nodes in the tree must have 0 or 2 children. Then we have a complete tree. For a complete tree, every level except possibly the last level, the nodes in those levels are completely filled with child nodes. An easy way to remember the complete tree is you fill the tree top to bottom and left to right. And lastly, we have a perfect tree. A perfect tree is a tree is full and complete at the same time. All nodes and all levels are filled. Next, we're gonna learn how to build our tree data structure, the tree in free form. First, we're gonna have the structure of a node. A node gonna have its data and an array of children because tree in free form can have as many children as it wants. And then we're gonna have the structure of the tree. It's gonna start with a root node and that's it. Surprisingly simple, right? Now let's see how our tree look like in real life. We're gonna insert our data into the tree. So first, we create a tree, and if we print it out, it's gonna be empty. Now we're gonna add a root node. So tree.root equal to node 1, and this is our first node. Then we're gonna add level 1 nodes. And because our tree data structure is so simple, there's no rule to automatically add the node into the tree. So we have to manually add it to the tree like this. So we have tree.root.children equal to the node we want. So if we print it out, our tree have root node and the first level node of 1, 2, 3, and 4. To add the level 2 nodes like 5, 6, and 7, we will also manually add the node into the tree. And if we print it out, we have 5, 6, and 7 at level 2 nodes. And this is the structure of the tree in our example. Next, we're gonna learn how to build binary tree data structure. When we hear the word binary tree, we know exactly that each of the nodes in our tree, we only have the maximum of 2 child nodes. So in our structure of the node data field is gonna be the same. And for children of the node, we have left and right, only 2 of them. So that's how a node look like. And now we build our binary tree data structure. And it's also surprisingly simple. It's only have root node. Now let's see how we use this structure to build our binary tree in the previous example. First, we create our binary tree, then we print it out. Of course, it's empty for now. Then we add the root node 5. So binary tree.root equal to new node 5. And if we print it out, we have our first node, which is 5. Then we can have level 1 nodes, 3 and 9. Root.left equal to node 3 and root.right equal to node 9. To see that our tree now had node 3 and 9. Next, we can add level 2 nodes, 8, 6, and 1. And as you can see, there's no rule to add the nodes automatically, so you still have to manually add it. This one here, root.left.left equal to node 8, root.right.left equal to node 6, and root.right.right equal to node 1. Then if we print it out, we have our level 2 nodes here, which are 8, 6, and 1. And we have created our binary tree like the example. This will conclude Tree Data Structure Series Part 1. Thank you for watching and I will see you in the next tutorial.